Okay. We'll start, Eva, if you sit down.
Yeah.
Okay, so it's a pleasure for me to introduce you to Alan Weinstein, who is going to talk about Hamiltonian Lie algebroids over Poisson manifolds.
Okay, well, thank you very much for this invitation, and I'm really sorry that I wasn't able to be there in person. As I was telling Cedric, that's better. Yeah, as I was telling Cedric, this is the first of the 2000 plus 2N Poisson conferences that I haven't been able to attend. I'm very sorry. I hope you guys are not suffering too much from the heat. I was told you have good air conditioning in the auditorium. I hope also in the residence. So anyway, the beginning of all this was the master's thesis that Stefano Ronchi wrote at Bonn with Christian Bloman, which took off from some earlier work that Christian and I did on setting up the notion of Hamiltonian Lie algebroids. And we did it over presymplectic manifolds. And the eventual aim was to apply this to the initial value problem of relativity, the initial value equations for Einstein's equations, but we never actually made it there. And that's still an open issue. But the subject of symplectic or the Hamiltonian Lie algebroid seemed to take on a life of its own, including some applications, or actually some input from some symplectic topology, even, which I'll briefly mention later on in this talk. So anyway, Stefano's assignment, so to speak, from Christian, I guess, either that or his initiative, I'm not sure, was to extend what we did to Poisson manifolds. And some new things come up that are quite interesting. And I'm going to talk about this development, and then Christian and I came in and joined the project, and we're now writing a paper on Lie algebroids over Poisson, Hamiltonian Lie algebroids over Poisson manifolds. This is still very much work in progress. And a part of it, as I said in the in the notes in the abstract, part of it was motivated by some remarks that Alejandro Cabrera made 5 years ago at a talk I gave at a conference in Banff. And I will go into some detail about that at the end of the talk. So, I'm looking at notes. I've never done it quite this way before. I have notes on the side that I'm looking at, and then I will start writing here. So the first example of interesting as a Lie algebroid is an action Lie algebroid, which is the action where G is a Lie algebra acting on the manifold M. And let's see, I can highlight that. G is acting on M, sorry. That gives a Lie algebroid. And now we're going to assume that M has a Poisson structure. And then there are three conditions that we could require of the action in sort of increasing sophistication or what. One is that the action, sorry, that's always a challenge. to preserves the Poisson structure. Pi on M. Secondly, then we just call it a Poisson action. Secondly, is that there's a momentum section, or well, the usual momentum map goes from M to G star, but we will think of it as a section from M to M cross G star, which is just the dual of the Lie algebroid. So a candidate for a momentum section, mu, we'll think of as a section, a candidate for a momentum section is based on a candidate from a momentum map. We'll think of it as a section of A star. And then the condition is that the usual one, that if we take the components of mu, that they're Hamiltonian vector fields, define the action, they correspond to the given action of the Lie algebra G. And the third condition is what one can call equivariance. Which is, if there were a group involved, it would be equivariance of capital G equivariance of the momentum map from M to the momentum map from M to G star, which we can interpret in terms of properties of the section here, which I'll go into a little bit later. So these are three increasingly restrictive conditions on an action. In the first case, we say it's a Poisson action. In the second case, we say it's a weakly Hamiltonian action. And in the third case, we say it's a Hamiltonian action. And of course, that comes from properties of the action itself rather than the Lie algebroid. The action preserves a Poisson structure. The action has a momentum map, and the momentum map is equivariant or infinitesimally equivariant. So what we want to do is translate those into conditions on the Lie algebroid. And so to go to the general case, okay, so let's see now, let's try this again. Where A is a general Lie algebroid, okay, so one. So we said that the action preserves the Poisson structure. So up in the action group-wide case. So if the action preserves the Poisson structure, we can interpret that as saying that the constant sections of the Lie algebroid, so we have this Lie algebroid A with an anchor map to Tm, so that sections of A go to vector fields. And not every, even in this case here, in the case above, not only does not every section goes to a vector field preserving the Lie algebroid, only the constant sections. And general sections don't go to general sections. General maps from M to Lie algebra G don't produce Hamiltonian vector fields or even Poisson vector fields. So for condition one already, we have to replace the notion of constant vector fields. So we have to introduce a connection D. And then what we have to say is that the Lie algebra, the Lie derivative by rho of A of pi equals 0 only if, well, first, in the first case where we have the trivial connection, the condition would be that A satisfies dA equals 0. But in general, if we don't have a flat connection, we don't have sections with dA equals 0. But we can always find sections with dA equals 0 at a point. And then we can require that the Lie derivative by rho of A be 0 at that point. So that turns out to be a good generalization of what it means to be a symplectic or a Poisson action to Lie algebroid. And so in this case, we say that the connection is Poisson anchored with respect to the Lie algebroid structure and the Poisson structure pi on M. The second condition, again, normally just for constant sections, is that if we take pi tilde, the associated map from cotangent vectors to tangent vectors, then this is the condition that mu be a the usual condition that mu be a momentum map, but it only applies to constant sections A. And again, we only require this then for sections which are constant at a given point. And then we require this identity to hold at that point. And the third condition is that there are various ways of writing it, but U paired with the bracket, the Lie algebroid bracket of the sections A and B is equal to rho of A times mu paired with B. And so again, in the Lie algebroid case, in the action algebroid case, this just holds for constant sections. And in our case, we require that it holds at a given point if the sections A and B are D parallel at that point, or D horizontal. In other words, have vanishing covariant derivative at that point. Okay. So there's another version of this, which is not a pointwise condition, and that uses something called the opposite connection. So if we have a connection on a Lie algebroid A, then the opposite connection turns out to be an A connection on the tangent bundle. And of course, in the case when A is the tangent bundle with the usual Lie algebroid structure, then this is what's traditionally been called the opposite connection in differential geometry. And it's defined by saying that dA acting on a vector field V is rho of dV of A. Remember that if in the tangent bundle case, rho is the identity, so this would just be the dV of A, interchanging V and A, but then we have to correct it in order to make it be a connection. And in this case, we corrected by the vector field bracket of rho of A with V. And again, if you just look at the case where rho is the identity, we get the usual notion of opposite connection. And the point of the opposite connection partly is that if the opposite connection equals the original connection, then that means the connection has no torsion. And one can always build a torsion-free connection out of a given one by averaging it with its opposite connection. Of course, here that doesn't make sense because the opposite connection is acting in different way on different spaces. Okay, so in terms of the opposite connection, then we have this nice condition that simply the opposite connection acting on pi equals 0. So the opposite connection originally was defined to act on vector fields or on the tangent bundle, but as usual, you can extend it to all tensors. In particular, you can extend it to bivector fields, and then the condition is d pi equals 0. The other conditions okay, sorry. The other conditions turn out to not need the opposite connection once the first one is satisfied. The first one is that pi tilde of the function, or rather, let's see. Yes. So d mu is a one form with values in the dual of the Lie algebroid. A is a section of the Lie algebroid. So together, this inner product is a one form, and we require that pi tilde of that be rho of A. So that's the general version, and it works for any section A. And the third condition is that the Lie algebroid differential of mu, which is a Lie algebra 2 form, so we can apply it to a pair of sections, A and B. That should be equal to pi of d mu paired with A, comma, d mu paired with B. Okay? Okay, any questions?
Are there any questions in the room? No, for now there are no questions. Yes.
I'll go on. So now the next thing is examples. Let me insert a page here. Okay. So the examples, the first example is a kind of trivial example of Lie algebra bundles. Oh, by the way, I guess it doesn't work. I'm going to have to stand up to show off the t-shirt that I'm wearing. I've tried to wear this to every Poisson meeting since my daughter bought it for me in Bogota many years ago. Anyway, Lie algebra bundles, that's just a bundle, a Lie algebroid where the anchor is 0. So the fibers are actually Lie algebras. And in that case, let's not number this because then it's confusing. Okay, so condition one, that's the version of action preserving the Poisson structure. It turns out any connection works. Basically because the anchor is zero, and so zero vector fields always preserve the Poisson structure. The second condition, which is the condition of mu being a momentum map, is that mu is horizontal along symplectic leaves. Obviously, that's not true for any connection. And in fact, for some connections, it will be the case that mu equals zero is the only momentum section. And the third condition is that mu annihilates any Lie bracket, any section which is the bracket of two sections. So in particular, for example, if a fiber is semi-simple so that everything is of the form AB, then mu must vanish there, and then by condition two, it must vanish everywhere on that leaf. So mu must vanish on any leaf with a semi-simple fiber anywhere over the leaf. There's no reason for the fibers to be the same over different points. Sorry, my computer is telling me I should move the screen up. Okay, so that's the case of Lie algebra bundles. In the symplectic case, obviously mu has to be horizontal everywhere on the manifold. There's only one symplectic leaf. And this third condition, in particular, if there's any semi-simple fiber, mu must vanish everywhere. Okay. So the second interesting case is that of the tangent Lie algebroid. Okay, so here we've worked this out for the symplectic case in the paper with Christian. Let me just go ahead and add another page right here so I have it ready. I can get rid of this. Okay, so for the tangent Lie algebroid, if D has torsion, that I'll use that notion for the torsion of D. And d pi equals 0. So if there's a torsionless connection, such that d pi equals 0. So it has nothing to do with the let's see, sorry. This is something called the A torsion, right? Because D is a connection on A, so not on. There's a notion called the A torsion, and if the A torsion is 0, then the condition is that pi be parallel along the fibers, along their symplectic leaves. And now I'm it's the tangent-Lie algebroid. Sorry. So it's the tangent-Lie algebroid. So the A torsion is the usual torsion, and d pi equals 0. Okay, along symplectic leaves. That's right. This is the tangent-Lie algebroid. Sorry. So d pi equals 0 along symplectic leaves, and that exists for sure whenever pi is regular. If pi is regular, then we can always find a connection such that it's parallel along symplectic leaves. Okay, so condition 2 for the momentum to exist, and here we see that things are starting to get for momentum section, which in this case is simply a one form. For the momentum section to exist, and then the momentum section can also be thought of as a vector field. And it turns out that because we already looked at the symplectic case, that this exists if and only if, that means there's a suitable section such that there's a momentum section for that connection. If either, if either M is non-compact or if it's compact, the Euler characteristic is greater than or equal to 0. And the point of that is that if the Euler characteristic is greater than 0, greater than or equal to 0, or non-compact, we can find a vector field whose zeros all have index 1. In fact, we can even fiddle it so that the zeros of the vector field all have they all look like the natural Liouville vector field on Euclidean space. And in that case, we can find a connection, building it up locally, such that d pi is equal to 0. Okay, and the third condition, and again, we must be in the symplectic case, there is a nowhere 0 Liouville vector field. And equivalently, we need to have a nowhere zero primitive. For omega, which is the symplectic structure that corresponds to pi. So that led to an interesting question of symplectic topology, which is when does a symplectic structure have a nowhere zero primitive? And it turned out that the condition is simply that it have a primitive. In other words, that the manifold be an exact symplectic manifold. In particular, that of course requires that it be compact. And that was work by, originally work by Shudi Tang. Some parts of it were done by Shudi Tang and Yael, then later with Yael Carchon. And also by Benno Stratman. In the case of Stratman, he worked directly with the primitive and got rid of the zeros. And in the case of Tang and Carchon, they found a non-zero Liouville vector field. And the idea there is to start with a Liouville vector field. This was kind of the original idea that Christian and I had. You start with a Liouville vector field and then try to remove its zeros by pushing them out to infinity. And it turns out that you can do that always. So anyway, that's, as I said, that's basically a question of symplectic topology. When can you find a primitive, when can you find a nowhere zero primitive for a symplectic manifold? Okay. So that's the end of the tangent Lie algebroid structure. And next is the cotangent Lie algebroid. So this is new for Poisson manifolds. In the case of a symplectic manifold, the cotangent Lie algebroid is just isomorphic to the tangent Lie algebroid by pi tilde. So here we have some new things happening. By the way, how much time do I have left?
You still have 35 minutes or 30 minutes.
30? How much?
30 minutes.
30 minutes. Okay.
Yes.
Okay, that shouldn't be any problem. Okay, so for the case of a cotangent Lie algebroid, the first condition is it turns out always by the dual of a torsion-free connection. So if we have a torsion-free connection on the tangent bundle, it gives a connection on all other tensors, and in particular, it gives a connection on the cotangent bundle, which we call the dual connection. And it turns out if the original connection is torsion-free, then the dual is always preserving of the Poisson structure. Secondly, now the second conditions are only sufficient conditions. We haven't worked out necessary conditions. The second condition, the second condition is, well, it suffices. To have a nowhere vanishing vector field but it has to be in the image of pi. Or pi tilde. So for example, if in the regular case, where the Poisson, where pi tilde has constant rank, a sufficient condition for this is that there be a nowhere vanishing vector field. In fact, necessary sufficient condition that there be a nowhere vanishing vector field tangent to the symplectic leaves. So that's kind of a topological condition. Now, as I mentioned, in the symplectic case, you can also have zeros of positive index, and it's not clear exactly what that means or how that translates into the general Poisson case. So that's an open question. And the third condition, again, sufficient, is a nowhere vanishing Liouville vector field. By Liouville vector field, I mean that the Lie derivative by the vector field V of pi equals pi, or minus pi, it doesn't really matter. Again, in the image of pi tilde. So this is a sufficient condition. Maybe it's necessary. Maybe it's necessary in this case. No, I think we have examples where it's not necessary, and we have no idea what the obstructions to this are. Okay. So now I want to go on to these comments of Alejandro Cabrera. But before I do, maybe I should ask if there are any questions.
Are there any questions in the room? No, people are happy here.
Okay. Well, I don't know about that, but anyway, let me go on. Okay. So these were actually notes that I made on my notes from the talk I gave in Banff, summarizing his comments so I wouldn't forget them. And it's taken us 5 years to get back to these questions, and we still don't have real good answers, but they're very interesting questions. And when I talked about it, it was in the symplectic case or the pre-symplectic case even, but it turns out that his questions really made most sense when there's a Poisson structure on the base. Okay, so the so the setup is I won't go, I will go through this anyway. I just wanted to show you that these are comments, and basically he had all the right ideas, I think. So the first thing is that if we have a connection on A, let's see. If we have a connection D on A, we also have a dual connection on A star, which I've already talked about. And that gives a splitting of TA into a horizontal piece and a vertical part, T of A star, rather. So that gives a splitting of tangent vectors, and we get a splitting of wedge 2 of tangent vectors, in other words, bivectors. Well, we can write that as things HH form HH plus HV plus VV. So these are strictly vertical bivectors. These are strictly horizontal bivectors. These are the wedge product of a horizontal with a vertical bivector, and so on. So you can do the same thing for trivectors and so on. Split them into this horizontal and vertical pieces. Now, if M has a Poisson structure, it then lifts to something that we can call pi HH. It's going to be a horizontal bivector field on T star of A. It lifts to pi HH. Now, in general, pi HH is not a Poisson structure. It's a bivector field. If the connection happens to be flat, then it's a Poisson structure. But in general, the bracket of pi HH with itself won't even be horizontal. It'll have vertical pieces that correspond, that involve the curvature of the connection. In fact, pi HH bracket pi HH is of type H is of type HVV. The HH parts go away because pi was a Poisson structure. So we're just left with the HVV part, which depends on the curvature. And there's a formula for it, which I won't write down. On the other hand, we also have, of course, on a Lie algebroid, a natural Poisson structure on the dual. On a star. We know that there's a natural Poisson structure on the dual of a Lie algebroid. And it anchors, actually, you don't even need a Lie algebroid to have a Poisson structure. So roughly speaking, if we have a Poisson, the Poisson structure is such that its vertical part is given by the bracket of the sections, and the horizontal vertical part is given by the anchor, and the horizontal part is zero. Anyway, it's always a Poisson structure, and if we just have an anchor, we can just write down a bivector, which is given by a horizontal vertical part, which is just pairs the horizontal part. It takes a vertical vector and pairs it with the projection of the horizontal vector. Okay, so anyway, we get a Poisson structure on the dual of the Lie algebra, or the dual of the Lie algebroid. And again, so now the idea of Cabrera was, first of all, to look at the pair given by the natural Poisson structure on the dual of a Lie algebroid and the horizontal lift of a Poisson structure on the base. And we can ask for such a pair of Poisson structures, or in this case, where pi HH might just be a bivector field, we can ask that their sum be a Poisson structure, or we could ask that their Schouten bracket be zero. And so the question is, how are the properties of this pair related to the question of whether we have a Poisson Lie algebroid? Okay. So finally, if mu is a section of a star, then mu of m contained in a star is a submanifold, of course, sort of containing the lift of pi. So if we have a section, we can take the pi on the base and just lift it to the section. Of course, that won't be a Poisson structure on the total space. It'll just be a Poisson structure on that submanifold. But we can still ask how that's related to the Poisson structure on the original, on the dual of the Lie algebroid, how it's related to pi a. So we want to relate this to pi a. And we don't really have any answer in the general case except some partial answers. But for an actionally algebroid, with the trivial connection, remember that's the manifold cross a fixed Lie algebra, and the connection is given by the flat sections or the constant sections. It does seem that that we have that the bracket of pi a and pi hh Schouten bracket equals 0 if and only if the trivial connection is Poisson anchored. In other words, if the action is Hamiltonian or the action is Poisson, action preserves pi. So this is a good step in the direction of showing how, and by the way, in that case, since pi hh is also a Poisson structure because the connection is flat, this condition is the same as saying that the sum of pi a with pi hh is equal to 0. That's the usual condition that we look at for pairs of Poisson structures. In general, if we don't have an anchor, if we don't have an action Lie algebroid, it looks like that the vanishing of the HHV part of this bracket here vanishes in the Poisson anchored case. And it's not clear what the other components give, but they involve the curvature of the connection. So it's not, you can't expect that this to be 0 for a general connection. And the vertical parts involve the curvature, the curvature of the connection. So that still remains to be worked out. And again, it's not completely clear how being a if we have a section mu, of course we could ask whether mu is a Poisson map. Because it is a map between Poisson manifolds. It's not clear how that's related to, although it should be somehow related to the conditions on mu being either a momentum map or an equivariant momentum map. So as I said, that's still mostly in work in progress. Again, we can look at sort of HV parts and compare them to see what's going on, but there's still computations that remain to be done. So thank you for your attention. Excuse me for not being there to do this in person, and I look forward to hearing any questions and comments. As I said, this is very much work in progress, and so comments are very welcome. Thanks.
Okay, thanks a lot, Alan, for this nice talk. Are there questions here in the room? I mean, as you see, if you ask Alan now a question, you will appear in the next Poisson conference. So there's a question here about Mario.
Yeah, hi Alan, thanks for the talk. So in your paper about Hamiltonian Lie algebroids, you mentioned the problem of finding a moment mapping relation for the Einstein constraint equations as a motivation for this object. So what is the status of this application?
Well, the status of this application is not very good. Well, there are two things. First of all, all the Poisson structures that are well, in the case of our original paper, all the presymplectic structures that we found that were natural on this space of initial conditions, or on the Lie algebroid that we found, that I should have said that earlier, that Marco Fernandes, Christian, and I found some Lie algebroids whose natural brackets, they're trivial bundles, and the brackets corresponded exactly to the Poisson bracket of the constraint functions in general relativity. So we thought we were really on the right track, but it turned out that any of the Poisson structures we constructed, or in that case presymplectic structures, were not presymplectically anchored with regard to any connection that we could think of that was relevant to the problem. So we then tried again with Michele Schiavina, and in that case we found a new Lie algebroid which was smaller than the old one, and it involved now super variable, odd variables. But again, we couldn't find a Poisson structure or a presymplectic structure that made that Hamiltonian. So that problem is completely still unsolved.
Thanks.
Okay, are there other questions for Alan? There's a question here. There are two questions here.
You consider three conditions for the definition of Hamiltonian Lie algebroid, but do you have some meaning to consider a part of three conditions that only some of conditions? Do you have a meaning?
I'm not sure I understand the question. Maybe.
Yeah, the question is, can we relax three conditions in some sense?
Oh.
Yeah, in some sense, the three
conditions. I don't know of any obvious way to relax those conditions that would be relevant. Now, one could relax the conditions, perhaps. No, I think one needs even stronger conditions if one wants to really be compatible with the picture that Alejandro Cabrera suggested of the two Poisson structures on the dual of the Lie algebroid.
Thank you.
Okay, there's one more question here.
Hi, Alan. Thanks for your talk. I just wonder if you might just briefly explain. I wonder if you could just briefly explain what your initial dream was for the Einstein equations. I don't really remember, and I'm sure people would appreciate hearing it.
Oh, okay. So the original dream was to take the initial value problem of the Einstein equations is a Hamiltonian system on the cotangent bundle of the space of three metrics. It's an evolution equation there, and it turns out to be a Hamiltonian system, but the initial conditions have to satisfy some constraints. So there's a constraint manifold within the cotangent bundle of the three metrics. And it's known that this has two properties which are kind of typical of the zeros of a momentum map. One is that it's coisotropic, and the second is that it's not a submanifold because there are singularities, but the singularities are very nice. It's just there. It's a product of a symplectic manifold with a finite dimensional cone in a finite dimensional vector space. So those are the conditions that that are satisfied by the constraints, and those are conditions that are known to be true for the hi, Margot. Those are conditions that are known to be true for the zero sets of a momentum map. So we developed a theory of Hamiltonian Lie algebroids where there's a momentum section, and the zeros of the momentum section, if it's equivariant, are coisotropic. We never did quite get to the part about the local conic structure of the singularities. So that's what we were aiming for, and somehow it seemed to be related to the symmetries. There are symmetries, obviously, the diffeomorphism symmetries of the Einstein equations, but they don't descend to symmetries in the usual sense of the they don't descend to symmetries in the usual sense of the initial value problem, because the diffeomorphisms of four space don't act on initial values in three space. So what we did find was a Lie algebroid with Marco Fernandes. We found a groupoid, actually, with the property that its Lie algebroid represented these sort of symmetries of the problem. But we were never able to get that to be a Hamiltonian Lie algebroid so that we could apply the general theory of Hamiltonian Lie algebroids.
Okay, thanks. So there's one more question.
That's all I have to say about Marco's question.
Yes, this is a question of Rui Fernandez. He asked, why not algebroids over Dirac structure? So the two cases, presymplectic and Poisson, merge. Any thought of that?
Yeah, we actually thought about that as a next problem, but we haven't actually done anything about it. It seems that just starting on it, it seems that there should be a nice theory of this, because there's a Lie algebroid structure associated with the Dirac structure. And so one can compare that with the Lie algebroid structure of a given Lie algebroid structure. But we haven't really done anything with that. But it is, I'm sorry, I actually meant to mention that. Thanks, Rui, for the question.
Okay. Some other questions? Okay, I think that's it. And so thank you very much, Alan, for this very nice talk.
Well, thank you for listening. I'm glad I had the
And
choice,
I don't know if
the
it's
chance to give
possible.
it.
Sorry, what did you say?
Do you see us?
Can the camera just pinpoint to us for a second? Yeah? Do you see us, Alan?
Where's the camera?
Or not?
He
He disappeared?
Did I disappear?
Okay.
Do you see us?
Do you see us?
Yes, I see Cedric and Ava.
Okay,
Okay,
great.
this is for you.
So, yeah, so we thought a great combination with your T-shirt would be don't put it on, it's for Alan.
Yeah, okay. I will clean it.
So we'll give you another cap than this one, but like with the same outfit, so that it suits very well with your T-shirt. So you don't see. Maybe you don't see it.
Unfortunately, I can't see it too well on the screen.
Maybe you don't see it, but it's a cap from the Poisson 2022. So that.
Okay.
in great combination with your T-shirt.
Yes, I will look forward to wearing that to Poisson 2024.
Exactly.
Wherever it is, I guess.
Looking forward to see you soon, Alan. Thank you for the talk.
Okay. Thank you, Ava. You're welcome.
Okay. So this is the cap that you'll get to Berkeley. Okay, and then there's
Okay, well, this is what it's supposed to go with.
Okay, perfect.
We'll arrange the call.
We arranged the colors. This is what Eva says. So you'll be perfectly styled for next Poisson conference. Okay, so this is everything for this afternoon. For the part of the Poisson conference. Okay, I remind you that we have another event now at the Residencia de Estudiantes just next to it. Okay. And there's one more thing that I would like to do, is to tell you that for the people that would like to come to the social dinner on Thursday, okay, there's one last chance to do this, and this is to see Andoni de Arriba, okay, and pay him the money for the social dinner. Okay, I mean, except for those that already did it, or except for those that are covered by the social mean. Okay, so well, see everybody at the Residencia de Estudiantes now.
There will be wine afterwards. Ahí está, no wine, es que como mínimo habrá que darles.